Example number 3, we're going to be working with hydrocyanic acid, HCN, and I've pulled the Ka and the pKa here. I'm just going to fill them in their respective spots. And let's see, pKa, I tend to put the pKa down here, 9.21. So we're asked to find what's the initial pH of the HCN solution. So an initial pH means no base has added and it is just a weak acid problem. So we only need the concentration of the weak acid. So I'm going to put that here. Now let's zoom in just a little bit over here and work this problem. So we have our HA, we have no initial H plus or hydronium ion, and we have no conjugate base. We're going to change this in order to establish our equilibrium. So we're going to change it by some value X. So we will add to the product side and subtract from the reactant side. So now we can set up our Ka expression, and our Ka expression at equilibrium, 6.2 times 10 to the negative 10 is going to be equal to the products multiplied together. So we have X squared divided by the concentration of the reactants multiplied together if we had more than one, but we only have the one. Now, our initial concentration is much more than 1,000 times greater than our Ka value. So that means we can simplify. And when we can simplify, that makes everything better. So we're going to take our 6.2 times 10 to the negative 10, and we're going to multiply that by the denominator, which is now 0.15. So X squared is equal to 9.3 times 10 to the negative 11. Now, in order to find X, I need to take the square root of that value. So I get 9.6, I'd call it 9.64. Why not? 9.64 times 10 to the negative 6. Capital M, molarity, is the unit. Now, you have to understand what that X signifies, and that X is the concentration of the hydrogen ion at equilibrium. So I'm going to fill that in here. And because that is in my calculator, it's pretty easy to punch the log button and then my answer button. So pH is going to be the negative log of this value, which would end up being the pH is 5.0, and I get a 1.5. So I'd call that 5.02 before any base is added. Yep, grabbed the wrong part. So then, what is the volume of KOH needed to reach the equivalence point? This is just a straight stoichiometry problem. So you need to know what the reaction is. So I have HCN, and it's going to react with KOH. Now you need to practice those skills. How do you predict the product? Well, the first thing you do with a weak acid and a strong base, you're going to make water. Then you make your salt. Salt is comprised of the cation of the base, which in this case is potassium, and then the anion of the acid, which is going to be cyanide. So potassium cyanide. Everything is balanced here, so we have a 1-to-1 reaction. That makes it easy. So I start with my volume. Oh, goodness. 4 significant digits. Volume of acid. And I'm going to just draw big lines because we're doing stoichiometry here. And then I'm going to multiply it by the molarity, forgot the L, of my acid. Then I convert my moles of acid into moles of base. Then I use the molarity of the base as a conversion factor in order to find out what is the volume of KOH needed. So I multiply across the top. 0.02 times 0.15 times 1 times 1 divided by the product of 1 times 1 times 0.1. And I get 0.03, and then I'm going to check my significant figures, 3 significant figures, 0, capital L, liters of KOH is needed for the equivalence point. Now that means that is 30 milliliters until the equivalence point. So this is before, this is at, and this is after the equivalence point. So let's do C now. What is the pH at the half equivalence point? Well, the half equivalence point is where we've neutralized half of the moles, or we've used half of the amount of base needed for the equivalence point, so 15 milliliters. So let's do I have, oh, I do. Okay. I'm going to need the volume, so 20.00 milliliters of a 0.150 capital M molar acid. And then I would use half of the base, so 15.0 milliliters, and my base is 0.100 capital M molar base. Now I can do this. So now I know I'm defined as being before the equivalence point. So I'm just going to use this stuff here. So I need to find out how many moles of acid I had to start with. So to find that, I take my volume of acid, 0.02000 liters, times my molarity, and I get 0.00300. That's moles of acid to begin with. Then I need to find how much base I have. So I'm going to start with my volume of base times its molarity. And I have 0.0015 moles of base. Now, just to double check, I had more moles of acid, or at this point, I have more moles of acid than I have of base. That means I am definitely before the equivalence point, but we defined it as being before the equivalence point. So I need to subtract the amount of base from the amount of acid, and that is the excess moles of acid. So I have 0.0015 moles of acid in excess. The moles of the base are going to be equal to the moles of the conjugate base. So my moles of base, 0.0015 moles of conjugate base. Now I can use the Henderson-Hasselbalch equation. So pH equals pKa plus the log of the ratio of A minus to HA. The pKa was 9.21. And the moles, we can use moles in the Henderson-Hasselbalch equation, of A minus is 0.0015. It's equivalent to the number of moles of strong base, because that's the limiting reactant in this problem. And then the moles of HA, the excess left over, is 0.0015 as well. Now the log of 1, which this ratio is equal to 1, is 0. So pH is equal to the pKa 9.21 at the half equivalence point. So that'll answer C. Now D, what is the pH of the solution after 20 milliliters of KOH is added? Well, we just have to make a couple of adjustments here. So let's see, I need to change this. O2O. This is going to change. And that means these are going to change as well. Now, the amount of acid that I started with stays the same, but now I have to recalculate my base. So 0.02 times 0.1, I have 0.00200 moles of base. I need to subtract these numbers. So I have the excess moles of acid I have is now 0.00100 moles of acid. The moles of my conjugate base are still going to be equal to the moles of my strong base, but now it's 0.00200 moles. So using the Henderson-Hasselbalch equation, the A minus over the HA, so I have my pKa of 9.21, plus log of this ratio, which is 2, and I get a new pH is 9.51 when I have 20 milliliters. So you see 5 measly little milliliters, and it changed my pH quite a bit. So what is the pH at the equivalence point? Well, when we are at the equivalence point, we are going to be governed by the concentration of the A minus. And that's going to be related to the moles of the base that were added and the total volume. So moles of base at the equivalence point. So I need 30 milliliters of my KOH, and then I have my original acid of 0.00300 moles. So I have 0.003 moles, but I have 50 milliliters. So the moles of the conjugate base, 0.00300 moles of my conjugate base, because it's equivalent to the moles of the base added. And at the equivalence point, the moles are equal. So I had already decided, or I had already calculated, that 30 milliliters, see my 30 milliliters, of my 0.1 molar KOH would be at the equivalence point. So that's how many moles of base I had. That's how many moles of conjugate base I forced. But I have a total of 50 milliliters in solution now, because my original acid solution was 20 milliliters. At the equivalence point, I need 30 milliliters of base for a total of 50 milliliters. So I need to find this new molarity. And I find that molarity by taking the moles and dividing it by the total volume in liters, of course. And I actually need 3 significant digits, but I'm trying really hard to keep it as friendly as possible. So the initial concentration of my A minus is 0.06 capital M molar. I have no HA and I have no O minus. Excuse me, OH minus. So now I need to create this equilibrium, and I'm going to change it by some value. That value is X. I'm going to subtract it from the reactant side, and I'm going to add it to the product side. But this time I'm going to be governed by a KB, not a KA. You only have a KA when HA is on the reactant side. HA is on the product side this time. So I need a KB. And in order to find a KB, what I do is I set my KB is equal to KW divided by KA. KA is 6.2 times 10 to the negative 10. 6.2 times 10 to the negative 10. So I take 1 times 10 to the negative 14, divide it by 6.2 times 10 to the negative 10, and I get a KB value of 1.61 times 10 to the negative 5. So my KB expression is 1.61 times 10 to the negative 5 is equal to the products multiplied together, x squared, over the reactant concentration, 0.06 minus x. We are really close to that 1,000 times bit, but you know what? I'm going to simplify just to see if it works, because it's pretty quick. So I take my 1.61 that's still in my calculator times 10 to the negative 5, and I'm going to multiply it by 0.06. And then I get x squared is equal to 9.6, I get 7, I'll call that 8, times 10 to the negative 7, but that value is still in my calculator. Then I'm going to square root that so that x equals 9.84 times 10 to the negative 4. But what's x? X is the concentration of the hydroxide ion. So because it's the concentration of the hydroxide ion, I can take the pOH. So I find the pOH at 3.0, looks like it's going to be 3.01. And then I can find the pH, because pH is 14 minus pOH. I get a pH value of 10.99 for this particular situation. But was that substitution, or was that simplification valid? Well, we use the 5% rule. So I take my x value of 9.84 times 10 to the negative 4, and I'm going to divide it by my initial concentration. 0.84 times 10 to the negative 4 divided by 0.06, then multiply that by 100, and I get 1.64. So because that is less than 5%, that is a valid approximation. So we can simplify that one, that's fine. So now the next part of the equation, or the problem, I should say, that was at the equivalence point. What's the pH of the solution after 40 milliliters of KOH is added? Well, when 40 milliliters of KOH are added, then we are beyond the equivalence point. So we have 20 milliliters at 0.05. We have 0.003 moles of acid. So let's remember that value. So the moles of acid to start was 0.003 moles of acid. But now I have 40 milliliters of base. So I have 0.004. I'm just going to double check that with my calculator because everything went go-flooey there for a second. So I have 0.004 moles of base to start. That means I have more base than I do acid. So I'm going to consume all of the acid, and I have 0.001 moles of excess strong base. That means that weak acid is not going to be affecting anymore. We are only working with the strong base. We had a 20 milliliter solution of acid to start with. We just added 40 milliliters of base, so my total volume is 60 milliliters. So in order to find the concentration of my hydroxide now, I take my excess base, which is 0.001 moles, and I'm going to divide that by the total volume of solution in liters. So divide that by 0.06, and I get a molarity of 0.01, and then I have a repeating 6, so I'll call it 0.67. So I'm going to solve for pOH. With this value still in my calculator, I'm just going to punch the log button, and I get a pOH of 1.78. That's not the answer, though. We're looking for the pH. pH is 14 minus that value, which should be 12.2. You could say 12.22. That's okay, too. No pun intended. And I think that's the end of example 3. It is. Let me know if you have questions.